Welcome to The Explainer. It's kind of wild when you think about it. How can scientists possibly know the exact shape of something as tiny as a molecule? Well, it's not guesswork. Today, we're going to become molecular architects. We're going to learn how to draw the blueprint that predicts a molecule's true shape, and really, its entire personality.
Okay, let's start with something we all know. H2O, water. But have you ever stopped to think about what it looks like? Is it a straight line? A triangle? The formula doesn't tell us. But the shape, well, the shape is everything. Let's figure out how to see it.
So what does it even mean for a molecule to look like something? Let's take a journey into this totally invisible world.
To really get a molecule, why water is wet or why CO2 is a gas, we have to build what I like to call a molecular blueprint. And this isn't just a simple sketch. It's a three-part plan that shows us a molecule's flat 2D structure, its actual 3D shape, and what we'll call its electrical personality.
All right, let's get our hands dirty. Our first step is creating the 2D floor plan. In chemistry, we call these Lewis structures, and they are all about one thing: electrons.
Now, we don't need to worry about all the electrons. We only care about the ones on the very outside, the ones called valence electrons. You can think of them like the hands an atom uses to connect with other atoms. They're the only ones that actually get involved in the action.
And drawing one of these things follows a pretty clear set of rules. First, you just count up all the available valence electrons from all the atoms. Then, you pick a central atom and connect everything with single bonds to make a skeleton. After that, you sprinkle in the rest of the electrons so every atom feels like it has a full set of 8. And finally, you do a quick double check to make sure you use the exact number you started with.
Let's give it a shot with ammonia, NH3. Okay, so nitrogen brings 5 valence electrons to the party. Each of the 3 hydrogens brings 1. That gives us a total budget of 8 electrons. So we draw our skeleton, add the last 2 electrons onto the nitrogen to make it happy, and there you have it. A quick count shows we used exactly 8. Perfect.
Okay, that one was pretty straightforward. But chemistry, it loves to throw a curveball. What do you do when you follow all the rules, but your electron budget just doesn't add up?
Case in point, carbon monoxide, CO. Carbon has 4 valence electrons, oxygen has 6. So our budget is 10. Simple, right? Well, if we just try a single bond and then give each atom its full octet to make them happy, we end up using 14 electrons. Whoa, we're 4 over budget. This blueprint is a total bust.
So what's the fix? The atoms have to share more. Let's try erasing some of those outer electrons and form a double bond instead. Okay, let's recount. And now we've used 12 electrons. We're getting closer to our budget of 10, but we're still not there.
All right, one more time. Let's make them share even more by forming a triple bond. We add the last few electrons, do the final count, and 10 electrons. It's a perfect match. We've found the correct 2D blueprint. So sometimes you got to do a little trial and error.
Okay, so we've got our flat drawing. Now for the really cool part. We're going to take this thing and make it pop into 3 dimensions. And this is where the magic happens, all thanks to one really simple but powerful idea.
It all boils down to this. Electrons are negatively charged. And just like those magnets you played with as a kid, they repel each other. They push each other away. In a molecule, they will always arrange themselves to be as far apart from one another as possible.
Here's a fantastic way to picture this. Imagine each group of electrons around the central atom is a balloon, right? If you tie just 2 balloons together in the middle, where do they go? They point in opposite directions. What about 3? They'll make a flat triangle. It's that natural repulsion that creates these incredibly predictable geometric shapes.
Chemists actually have a name for the total number of these balloons or electron zones. It's called the steric number, or SN for short. And calculating it is super easy. You just count the atoms bonded to the center, plus any lone pairs of electrons sitting on that central atom. This one number is the key to the whole 3D puzzle.
Let's see this in action. For carbon dioxide, the steric number is 2, so boom, it's a straight linear molecule. Methane, CH4, has a steric number of 4 with no lone pairs, so it creates this perfect 3D pyramid shape called a tetrahedron. But then, look at water. Its steric number is also 4, but 2 of those are lone pairs. So those invisible balloons are still there, pushing down on the hydrogen atoms and creating that famous bench shape we all know and love.
So now that we have the 3D shape, we can add the final, crucial detail to our blueprint, the molecule's electrical personality. And it all comes down to an invisible game of tug-of-war.
Right. This tug of war is called electronegativity. You see, some atoms are just greedy. They're electron bullies. They pull way harder on shared electrons than other atoms do. It's basically their pulling power in a bond.
And by looking at the difference in that pulling power between two atoms, the delta En, we can see just how lopsided the game is. A small difference, like in a carbon-hydrogen bond, means they're sharing pretty evenly. But a big difference, like in a carbon-oxygen bond, oh yeah, oxygen is winning that tug of war big time. And we show this on our blueprint using a special little arrow called a bond dipole. The arrow always points toward the stronger atom, the winner of the tug of war, showing us exactly where that negative charge is building up. Okay, let's put it all together. Let's see how the 2D drawing, the 3D shape, and those little tug-of-war arrows combine to determine a molecule's entire identity.
And here it is. This is the moment it all clicks. Look at carbon dioxide. It has two strong tug-of-war arrows pulling outwards. But because the molecule is perfectly linear and symmetrical, those two pulls completely cancel each other out. It's a stalemate. The result is a non-polar molecule. Now look at water. It also has two arrows pulling, but because of its bent shape, they both pull in the same general direction. They add together, creating a net pull. This makes water a very polar molecule, with a negative side and a positive side.
And that final property, that polarity, is exactly why oil, which is nonpolar, and water, which is polar, will never mix. It all comes back to the blueprint we just learned to draw. So now that you know the rules of molecular architecture, think about it. What other everyday mysteries can you suddenly explain?